Hello Math 1093, this is Dr. P with iHeart Polar Coordinates. In this video we're going to talk about how to graph an example of a function, this function, in polar coordinates. Now sometimes when people introduce this topic they will talk about this function here being an example of a polar function. It's not really a polar function, it's just a function. Functions are functions no matter where you graph them. This function, I could have called it f, and it would have looked very familiar to us. F of theta equals 3 minus 3 sine theta. Okay, the fact that I'm calling the independent variable theta and the dependent variable r is just, I don't know, it's just a nice symbolic marker of what we're going to do, which is that we are going to graph this function in polar coordinates, which means rather than treat this as an independent variable which is graphed along the horizontal axis, and this is a dependent variable which is graphed along the vertical axis, instead we're going to treat this theta as an independent variable which is graphed as a measure of direction or bearing, and this r as a measure of distance from the origin, which is still the dependent variable. Okay, so we're going to graph this in polar coordinates, but it really is just an ordinary function. An ordinary trigonometric function, which may seem far from ordinary. Anyway, the approach we're going to take in graphing this, though, is going to be similar to what we would do if we were just starting to learn to graph trigonometric functions in the Cartesian plane, which is we're going to build a table of values and see what we can figure out about this function's behavior. So let's build a table of values for theta and r of theta, which is 3 minus 3 sine of theta. There we go. Now, when doing this, it's useful to write down a few key values of theta for which we can easily compute the output. So examples of those would be things like 0, pi over 2, pi, 3 pi over 2, and then 2 pi. I'm actually going to use a few more values here, just so that I have a little bit better shape, or better sense of the shape of the graph of the function. But really, we can do a pretty good job just by looking at these 5 values here. Like, we can get a pretty good idea of what's going to happen just from looking at those. So we're going to compute those values by hand, and then we'll circle back and figure out what the values are at those multiples of pi over 4. And we'll probably use a calculator for that. Okay, so anyway, well, when theta is 0, what is r of 0? R of 0 is going to be 3 minus 3 sine of 0, not theta, 0, which is just 3. And at pi over 2, I get r of theta equals 3 minus 3 sine pi over 2. Sine of pi over 2 is 1. So I get 3 minus 3, which is 0. When theta is pi, r of pi is going to be 3 minus 3 sine of pi. Sine of pi is 0, so I get 3 again. At 3 pi over 2, I get r of theta equals 3 minus 3 sine of pi over 2. 3 pi over 2, sorry. Sine of 3 pi over 2 is negative 1. So I'm going to get 3 minus 3 times negative 1, that's 3 minus negative 3, that's 6. And then at 2 pi, that's going to be the same as if I were evaluating at theta equals 0, because this function has a period of 2 pi. Sine of 2 pi is 0, so I should get 3 again. Okay? So I'm going to go and graph the points corresponding to those. When theta is 0, remember I'm graphing along this direction when theta is 0, and I should be at r equals 3. So I'm going to put a little point there. R equals 3, theta equals 0. When theta is pi over 2, my radius is 0. So in that case, I'm sort of looking out in this direction here. But when my radius is 0, I'm just stuck at the origin. So I have a point there as well. Okay, and then after that, when theta is equal to pi, I get r equals 3, so I'll have a point out in this direction. I realize those are in degrees, but you can. I hope by now you can code switch between degrees and radians. When theta is pi, I'm out in this direction, and I'm out a distance of 3. And then, let's see, when theta is 3 pi over 2, I'm out in this direction, but I'm out by a radius of 6. 1, 2, 3, 4, 5, 6. I believe I'm out there. All right. Now, just to get a better idea, I'm going to calculate values of r at these other values of theta, pi over 4, for example. So 3 minus 3 sine pi over 4 is going to be, let's see, it looks like that's 0.878, okay, or 0.879. So I'm going to write that down, 0.879. Okay, sorry, I'm just going to do a little calculator work here. It's going to be boring to watch. 3 sine 3 pi over 4, let's see, that's going to give me 0.879 again. Perhaps I should have expected that. That's 0.879 again. Yeah, really I should have expected that, because at pi over 4 and at 3 pi over 4, the sine function has the same value. Okay, and I know that's also going to be true at 5 pi over 4 and 7 pi over 4. So now I know better, okay? So I can save us a little bit of time. 3 minus 3 sine 5 pi over 4. That's going to come out to 5.12. It's interesting. 5.12. So that will also be 5.12. All right, so let's graph those points. So when I'm out in this direction, I'm out just a little bit less than 1 unit on the radius. So I'm going to be pretty close to the origin here. And then same over here. Okay, I think those are the right lines, right? Those are, yeah, it's hard to tell with so many grid lines here. I actually would prefer a bit fewer, actually. When theta is 5 pi over 4, I'm out in this direction, and I'm out by a radius of a little bit over 5, which is pretty generous. So I'm out here, and then same when I'm at 315 degrees, or 7 pi over 4. Okay, so now I'm going to just connect these dots the best I can and create a graph. Okay, so remember, I should be going through all these points. So I should be going through here, and then through here. Okay, can you all see that? And then through here, and then through here, and then back to theta equals 0. So let's connect those up. All right, I feel like there should be music while I'm doing this, but I'm not a very good singer, so I think I'll just draw instead. Okay, sorry, that should not be curved inwards there. It's just my drawing. All right, so the shape I should get is, so I'm just going to flesh this out a bit. It should be symmetric across this line. If it's not, it's just a defect of my drawing. But I get what looks kind of like, a heart shape. Perhaps that was planned. Anyway, I don't know if it looks, so actually officially in mathematics, this shape is called a cardioid. And that comes from the root word card, which stands for heart. If you're not convinced, consider the word cardiac, like as in cardiac arrest, which is what I'm about to have from this drawing. So this is a cardioid, which is a mathematical term for a heart shape. As you can see, it's not perfectly heart-shaped. Like there's no point down here, for example. It should just be a smooth curve. Maybe it looks more like a tomato shape. Perhaps it should be a tomatoid. But anyway, that's an example of how we graph a function in polar coordinates, and we'll be doing some more of these together in class.